All right, are we up? Looks like we are up. Let's go. Right. So, if you remember from before, we actually found a very nice repo. We found a nice repo from Facebook Research. I had submitted. There was an issue raised to add support for the LLaVA model. And I didn't get a response from the initial author of this issue, so I'm actually just going to implement it myself. So I'm actually quite excited to implement this. I've never worked with multimodal, um, a multimodal model before, so this will actually be a lot of fun. Go to hold on. I want to go to, oh, there's even code as well. So this is nice. We'll have a lot to we have a lot to pull from when implementing and adding support for this. It seems like if we go back here, it seems like just adding the model to the model's directory is a good first start. We have clip visual encoders. And then the bulk of the work for the model should be to add the LLM. A couple pointers to help with that. The decoder layer, root mean square norm, and then rotary positional embeddings, which is still a PR. I don't know if this is merged. Doesn't seem like it has been merged. It's still open. So we can probably set that as like a flag to change it or something like that. We'll see. All right, all right. So, without further ado, 1 second here. Let me SSH in to my server real quick. All right. Save. Go to multimodal. All right. Models. So we have all these video GPT, masked autoencoder modules, encoders. What's the okay? Fusions, attention, layers. Okay, losses. That's okay. Masking, optimizers. All right. Let's first make a branch here. Or actually, hold on. Conda create modal. Does this say what? 3.7, 3.8, 3.9. Okay. Actually, I don't want to. Bruh. Conda create. Torch multimodal Python equals. So anything greater than or equal to 3.8, I'll use 3.9. Python. Okay. Yes. And then conda install. I do want CUDA. PyTorch, Torch Vision, Torch Audio, PyTorch. Oh wait, but I think it's busted. Yeah, I forgot. Why is there? Damn, do I need to fix this first? All right, let's go. Build to initial VML. Driver library mismatch. No way, it's just a reboot. Damn, I gotta reboot my server, bro. Alright. Alright, we'll wait. Yeah, I forgot that my driver was all weird. So let's just give it 1 sec. And obviously I'm on a VPN, so good luck trying to get into this without the configuration. Alright, what's good? I have 1 viewer. What's good, 1 viewer? Was Bracken 1 viewer? Nothing? Alright, I'll just talk to myself. Dono wall, bro. I absolutely hate programming on Windows. That's why I have a server. I have a dedicated server specifically for development. It's an Ubuntu server. Has GPUs, has a bunch of nice stuff. It's so worth it. I literally just use this mainly for gaming and obviously streaming now. But in terms of actual development, you will never catch me doing actual development on a Windows operating system. Never, 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 never. There was a part of me that wanted to originally dual boot, and actually I can dual boot. I do have a small SSD that has Ubuntu, but the resolution got all messed up, and I don't know what I did, because it was just one day it was working fine. I was able to get, I have a 1440p monitor here, and I was able to, you know, have full resolution, full frame rate, everything. And then I boot one time, and then it just gets busted. I don't know what happened, so I just stopped. So yeah, there's that. I have a 3090, which is nice. Founders Edition. Shout out. Come on, bro. Reboot slower. No, please take your time. Let's see. I'm interested in lava. We can start looking at lava while we wait. Because I haven't gone through the paper fully. Oh, what is this? HTML? So we have a vision encoder, and then a linear projection, and then the language model, and then this encoded and projected representation is fed jointly into the language model to get a language response. Now for training, we might have to consider, I don't know if we have to consider their training paradigm for the multimodal training, because this is used for training at scale. Maybe we could just start with support. I think let's not make things too complicated and ditch this training paradigm for now and just focus on implementing the model itself. Are you up? Come on, bro. Okay. Bro, Eminem, shut up. Holy. I guess, dude. I guess we'll just start here. This specifically is what we're going to be focused on. Now, obviously, their figure is very nice and tidy, and at its core, it is rather simple. You take the image, take the language, encode and project. What's Z of V again? The visual features, and then HV is we apply a trainable projection matrix to convert Z of V into... Oh, I see. We got to follow the arrows. Okay, I see. So the projection is only for the image then. Whereas X of Q, which is the query, I assume, is just encoded? Perhaps. I think it's just directly encoded. And then we get the... Oh, so then H of V is W.ZV. Okay. With ZV being G, where I assume G is the encoder. Yes, it is. It is provided by the visual features, the grid features, before and after the last transformer layer are considered. Huh? Okay. We consider a simple linear layer to connect image features to the word embedding space. Specifically, we apply the matrix. Okay, so we use clip, encode the image, and then project it. And then we get the... Why H? Like hidden? Like is the hidden... We're in the hidden state? It's a hidden state, hidden space? I don't know. One thing when I read papers is that I'm always trying to understand obviously what they're talking about specifically. But honestly, one of the most important things to know when you are reading a paper is to ask yourself, why did they name this variable what they named it? Why are they using this terminology specifically? That is so important, because if you can make that connection, then it's no longer just variables and math. It's very much um, a simplified language of what they're doing. And that's really tough. If things are named poorly, you're done. Good luck. It's Jover. GG. But if the researchers or the authors of the paper are able to name things rather straightforward, or they're following a paradigm that is kind of established in a domain, in a niche, then it's not too bad. It really isn't that bad. Please work, bro. All right, let's go. Please work. Please work. Please work. Please work. Ooh. All right, we got our GPUs. All right, yeah. What was I doing? Oh, I was installing the repo, dude. All right, dude. All right. NVIDIA. What is my? All right. So conda install PyTorch, Torch Vision, Torch Audio, PyTorch CUDA equals 12.2. C PyTorch nightly. C NVIDIA. Why? You'll just on. Wait. Oh, do I need to? Yeah, PyTorch CUDA. That's what I did. 12 point. I have 12.2. Oh wait, I'm in base. Oh, thank God that failed actually. Conda activate. Torch multi. Why? Oh, PyTorch nightly? Sick, dude. Absolutely sick, dude. PyTorch. PyTorch. Please work. If I fail installing it, it's over. PyTorch CUDA 12.2. Can I just use 12.1? Even though I have 12.2? Hopefully. I mean, if I have 12.2 and then PyTorch CUDA is 12.1, I don't think that'll be a huge issue. That shouldn't be an issue. Yeah, okay. Let's go, dude. We're installing. How did they implement clip? image transform, and then torch stack. Okay. Oh, that's how you transform. All right. Take your time, bro. So I'm not gonna lie to you when I say that this is very much outside of my comfort zone. I've actually never contributed to open source, and so I really am just kind of jumping in the deep end here. But that's just kind of how I've always learned. And so, you know, if I fuck up, I fuck up. That's fine. But you know, I've never actively worked on a multimodal neural network, although I'm pretty comfortable with neural networks. And I've never really contributed to open source, although I am comfortable with coding. So I think this is it's natural. It's a very natural next step, and this is how you kind of have to be, I feel like, to grow as a researcher, as a programmer, whatever it is. You have to constantly throw yourself in the deep end. This is kind of the only way that I've ever learned personally. Dude, take your time, please. So much to install, bro. So what's in clip? Image encoder, the model, and then the text encoder. And then what's in there? Init? Nothing. Okay. Okay. In clip, init. Okay. So models. What I'll do is I'll create a new directory. Well, let's finish this first, and then I actually have to create a new branch. Okay, great. Get status. Get branch LLaVA. Check out LLaVA. Models, and then let's create a new file here. All right. Let's go here to this init. I'll call this model.py, even though we won't really have anything right now. And then let's go back to the network here. So for the input image, we consider the pre-trained clip visual encoder. Well, let me see clip or LLaVA, the LLaVA model here. Model. Let's see the multimodal. So they have the clip, and then what's the builder? Okay. Clip encoder. model, language model. And then they have different ones. Okay, cool. So it supports different ones. What's in the LLaVA architecture? Here we go. You have Vision Tower. Initialize vision modules, unpad image, and then LLaVA meta for causal LM. Encode images, prepare inputs. Model encoder and projector. What's the builder here? Identity map, simple res block, linear pre-norm, and the projection back onto. Okay, so this is a residual. Okay. Let's go to so many tabs open. The projection W. The projection W.ZV, the grid features before and after the last transformer layer. We consider a simple linear layer. All right. Okay. But is it a simple linear? Or is it linear? Jello linear? Ideally, if I implement the model correctly, I should be able to just bring the checkpoints and copy them over to the architecture that I built. Projector weights. So let's start. I mean, honestly, I'll just start with a skeleton. Bro, where's my extensions? Yeah, why isn't it? Oh, because NN. Okay. Let's see how they integrate this. And they do it as an NN module. Okay, great. Image encoder, text encoder. Okay. So we will have I don't want to deviate from how they do this too much. So image, text. You know, I do obviously want to follow we'll start with this. And then they have it to output, which I assume is a data class, the name tuple. Okay. And then all of these. I see. So image encoder. Text encoder. And then image to MM. What is LLaVA? I mean, it is Flava, but like, nah, I'm looking for something else. Google. Yeah, what's MM? Image text. Oh, multimodal encoder. Okay, so we don't need this then. And then what's image? We will need an image projection. All right. And then what we can do is then go data to embeddings. Okay. So then let's start with this. Happening. What? Go. Why though? Can I do it through? There's no remote branch. Would you like to publish this? Okay. Okay. So, okay. Oh, is it because? Oh, no. Okay. Check out main. Get branch. Okay, I see. New folder. LLaVA. File. And then init. All right. Oh, I'm committing. I'm not adding. Oh my god. And let me. So now, okay, great. And then if I go to PRs, I will delete this. Go back to my profile. So Alright, I'll just create the PR and delete it. Done. Alright, cool. Alright, let's go back to this. So we have, if we have the image encoder, and then the text encoder, and then the image projection. So ideally, self.image, let's say encode and project image, and then we will feed in the image here. Image embeddings. settings, and then this should just be the text encoder of text. And then, are they concatenated? Embeddings? And then pass through language model. And then return response. Okay. Encode and project image self. I guess this technically has to be optional. And then I guess this should return a tensor. And so if we do self.image image encoder of image image, I mean, I ideally we could just return image projection of the encoder. Ideally. Okay. And then we have a sequence of visual tokens HV. More sophisticated schemes to connect them can be considered, such as gated cross attention, Q former. We leave exploring more, just future work. But what do you guys do? I guess we have the code. Let's go to the code. So many issues. I mean, yeah. This is the multimodal project. That's done. Okay. Look at the model. This is the meta model. Oh, so there is a multimodal. Okay. This is ABC. Okay. So I guess we could theoretically we will say connect embedding. Joint. I'll call this joint representation. So what's Q-former? What do they call Q-former here? Extract visual features from the frozen image encoder. Fucked right. I guess this is the multimodal encoder. Let's go. Also, fix the settings. And then this should just be tensor. And then text embeddings should also be tensor. And this will also output a tensor. And then here, I'll call this, yeah, this is joint representation connection is not the best name, but connection equals joint. but it makes sense to me. And then if anyone makes comments in the PR review, then I'll change it then. Joint representation connection. But this, I mean, this could just be the multimodal. Here they have the multimodal encoder. So I may have to do something like this as well. And then, let's see. So what do we add? I'll just say continuing the skeleton. Okay. Okay, cool. Let me quickly run to the bathroom, grab some water. Drink water. Stay hydrated. All right. Let's see. So I may have to. Shall we go through this model or this paper rather? I think this may be worthwhile. So I'll take notes as well on the side here. All right. I mean, actually, I might prepare this for another time. Okay. Actually, what I will do, since the hour is up, I did want to spend the next hour. Wait, no. Oh my god, my dyslexic ass. Okay. I did want to go through one of Meta's new model called V-JEPA, video joint encoding, joint embedding prediction. So joint embedding predictive architecture. Okay. As humans, much of what we learn about the world around us, particularly in our early stages of life, is gleaned through an observation. Take Newton's third law of motion. Even an infant or a cat can intuit, after knocking several items off a table and observing the results, that what goes up must come down. You don't need hours of instruction or to read thousands of books to arrive at that result. Your internal world model, a contextual understanding based off of a mental model of the world, predicts these consequences for you, and it's highly efficient. V-JEPA is a step towards a more grounded understanding of the world so machines can achieve more generalized reasoning and planning, says Meta's VP and Chief AI Scientist, Jan LeCun, who proposed the original joint embedding predictive architectures in 2022. Our goals is to build advanced machine intelligence that can learn more like humans do, forming internal models of the world around them to learn, adapt, and forge plans efficiently in the service of completing complex tasks. So I'm going to jump straight into the paper and kind of talk about what it is they aim to do, and kind of go through the mathematics just a little bit. So as we know, they seek to answer the simple question: how effective is feature prediction as a standalone objective for unsupervised learning from video with modern tools? So this is kind of the technical, formalized question that they are asking, given the prior article, kind of the background that we just read. And so really what they're trying to do, let's first go to this figure here. The overarching goal here is you take X and you encode it, you take Y and you encode it, and I'll describe what X and Y is, as well as Z, and you predict. Now this prediction gives an output of S hat Y, which is actually the features of Y. So what you're trying to do is give an X, you predict the features of Y, and then because you already know what Y is, and you have the encoder of Y, you kind of have this ground truth, and then you calculate the distance, or rather the loss. So what is X, what is Y, and what are these encoders, as well as what Z is. So what they aim to do is where is it? I had a nice. All right, so we'll rely on this figure. So the idea is that let's say you have an image. Now obviously this is a video, but we can generalize this quite easily. You have an image, let's say that's 256 by 256. This is X. This is just your image. We won't call this X because I want this to be aligned with the paper. If I randomly mask out specific portions of this image, so this part is masked out, and then we know what the information here is. This is X. Okay? Y. So here it is. The main idea is to predict the representation of an input Y from the representation of another input X. The basic architecture is made up of an encoder. Okay, blah, blah, blah. Which predicts the representation of y from the representation of x conditioned on a variable z, indicating the transformation or corruption. So if we mask out specific portions of this image, and we have some information here, so this this information here is preserved. That's going to be x, which means that y is actually going to be y will have this information, whereas this part is going to be gone. This is going to be y. And then z is actually, in this case, going to be a binary mask. Sorry. Where this will be, let's say, 1, 1, 1, 0, and 1. And this will all be 1. Okay? So z is the binary mask, the actual manipulation done to x. X will be the masked image. And then y is going to be the remaining of the masked image. And the overall objective here is that if you have this masked image, you feed it into a trainable encoder. So we'll say what they call it here is E of theta. And then you get some feature space representation, some embedding. And then you feed y into what we call E theta. Now, it's not going to be the exact same encoder, and we'll actually go over y in a second. But so this will be, let's say, the embedding of x, the embedding of y. In this case, they call it S of y. So let's do that. So you have S of x and then S of y. And the idea is to train this network, train the encoder, as well as the predictor, such that we feed in the prediction of S of x and S of y. So we're trying to minimize this. They call this phi. Because S of x is ideally, in an ideal sense, S of x is going to estimate for the features of y. So S of x ideally should be as close to S of y as possible. So this is the overarching goal here. Now, a couple things that we need to consider. Number one, why wouldn't the encoder, assuming we use the same encoder, why wouldn't we just always output zeros, right? Because if the overarching goal is to minimize the distance between these two, well, then we can just always encode them to be zero vectors, and then our distance, the prediction of 0 and 0 is going to be 0, which means that the loss of 0 is going to be 0, right? So like if you just have zeros all the way down, you have a supposedly perfect network, right? Obviously, this shouldn't be the case. We know in definition this is what is called model collapse. And they discussed this briefly. So we want, where was it? So we train our visual encoder, E of theta, to satisfy the constraint that the representations computed on one part of the video should be predictable from representations computed to another part of the video, which maps the representation x to the representation of y is trained simultaneously with the encoder. So the prediction network, the prediction of the encoded x, the output of the encoding, should be as close to the encoding of y as possible. And it is provided with the specification of spatiotemporal positions of y through the conditioning variable z, which they define as delta y. So naively implementing, so what they're doing here is they're optimizing. So we see minimize theta and phi. So now when we see this, we have to ask, what does theta represent? What does phi represent? So if we look at this formula here, anytime you see minimize and then some variable, this is what we're training, okay? So we see P of phi, E of theta, x delta y, minus E of theta, y. And then this is going to be an L1 loss. So immediately when we look at this, we know that this is the predictor network. So if we look at this, so we are optimizing the predictor. This is number one. So we're optimizing the predictor. And we know that the predictor ideally is going to map the encoded x, the representation of x, to the representation of y. So this, we have to train this, as well as E theta of x, which is also E theta of y. So we also have to train the encoder. Okay. So now we know what we have to train and kind of the paradigm in which we have to train it. However, as they say, this would admit a trivial solution where the encoder outputs a constant representation. So if we go back here, regardless of its input, right? Because if you train it like this, and you're saying, yeah, we want to minimize this regression, well, the network over time will figure out that we could just slash everything to 0 or 1 or 2, doesn't matter. I use 0 just because it's always a simple example. But this could be any constant value, because if we encode to a constant value, irrespective of the dimensionality, and the outputs, irrespective, always end up being all zeros, all ones, all twos, then the distance is going to be 0. And that's what matters the most. The distance being 0 is the ideal solution. But as we know, if we just always have constant values, then the encoder is useless. We're encoding meaningless values that is completely independent of your input. This has no value. This is meaningless. Okay? So, how do we prevent representation collapse? What they do here is rather simple. We have, let's go to this eraser. We have this function that we need to minimize. What they propose, which I'm not going to lie, I did not fully understand the theoretical motivation. So if you're interested in learning more about this, please read this on your own. I didn't fully understand it, and I also didn't have time to go through what they cite. So perhaps this paper, Grill et al. From 2020, the BYOL method is probably going to heavily impact their theoretical motivation. So I heavily implore that if you're interested in the theoretical motivation behind this, to read this paper. I didn't have time, and I didn't fully get a grasp for it when skimming through this section here, so I will be skipping it. Anyways, to prevent the representation collapse, what they do is say, we will train the encoder over X, which means that this will be P of E theta X delta Y. And what we will do is put a stop gradient operation, which I will define in a second. And we do an exponential moving average of the encoder onto Y. Okay? So, we will train the encoder. We will be training the encoder over X. And after, what is this? Does it say after every number of steps? So let's say after every 10 steps, for example, 1, 2, 3 steps, doesn't matter. After every n steps, we will take the exponential moving average of E theta. And we will call that E bar theta. And we will use this exponential moving average to serve as Y's encoder. And to ensure that there is no funny business happening where somehow the network learns that, again, if the average of the average of ones is gonna be one, or sorry, the average of zeros is just gonna end up being zeros, and then we get a representation collapse, we will implement a stop gradient. So this is not actually going to be trainable. That's the idea of a stop gradient. That's what they mean by stop gradient. So this means that it does not backpropagate through the argument. And E bar theta, as we just said, is an exponential moving average of the network E theta. This has been a collapse prevention strategy for image pre-training and studied empirically and theoretically. In fact, the objective in equation 1 is similar to the loss of this paper here used for image pre-training, but we modify it to an L1 regression, which we find to be more stable. Okay. So now we have kind of this framework. I'm going to skip the theoretical motivation here. And so now we have kind of this framework of training a network that not only will encode, if we go back here, that will only encode both your X and Y values, which are different parts of the same video in this case, as well as kind of the binary mask that is applied to the video. So we are not only training this encoder, but also training a predictor that will try to minimize the distance between the representation. We'll also train a predictor that tries to mimic. We train a predictor to try to map the encoding of X to the encoding of Y. Okay. Sorry, I struggled way too much on that explanation. So this is the prediction task, predicting Y from X. The feature prediction task is based on a masked modeling formulation, i.e. regions from X and Y from the video are sampled using masking. To sample Y from a video, we sample several possibly overlapping, spatially continuous blocks with various aspect ratios and repeat the spatial blocks across the entire temporal dimension of the video X. X is taken to be the complement. Okay, so this is kind of what we posed here. Masking a large continuous block that covers the full temporal dimension limits information leakage due to spatial and temporal redundancy of videos and results in a harder prediction task. So in this case, we've been looking at images, right? So if I mask out, if I have this this mask here, so let's go back to the Z, which was, again, 256 by 256, and the mask here. This is 1, and then where I highlight is 0, let's say. This is the case for the image. So what happens with a video? Well, we already know that videos are just framed images. So if this is going to be the same, if this is going to be a recording, so we're taking a bunch of frames per second, all we have to do is just take the same mask here and then apply it all across time. So this is our time, and then that's height and width. So the mask is going to be continuously applied in the same places across time. And this is kind of the idea here. And this is to prevent information leakage, and it results in a harder prediction task. We leverage two types of masks: short-range masks, where we take the union of 8 randomly sampled target blocks covering 15% of each frame, and long-range masks, where we take the union of two randomly sampled target blocks covering 70% of each frame. In both cases, the aspect ratio is randomly chosen in the range of 0.75 to 1.5. Given that both short-range and long-range masks are produced by sampling many blocks and taking their union, the result is an average masking ratio of about 90%. Okay. And then here they kind of go through so what matters for learning representation from video. Here they go through kind of predicting representations versus pixels. And what they show, and they even mentioned this earlier in the paper as well, models trained with feature prediction are superior to pixel prediction approaches and are competitive under full fine-tuning while using significantly shorter training schedules, and they're also more label efficient. So this is kind of one advantage of using this methodology, as we see here. And they show when compared to Vision Transformer that, wait, sorry, I may... Okay, so we use a Vision Transformer as our video backbone. To process a video with the Transformer network, we split the video clip into a 3D grid of L spatiotemporal patches, where the patch consists of 16 by 16, spanning 2 consecutive frames. We refer to those spatiotemporal patches as tokens. Okay, cool. So their tokens are going to be 16 by 16 by 2 blocks. This sequence of tokens is then directly processed by the stack of transformer blocks. My bad. Where was it? And then it inputs X and Y correspond to the masked regions of a video. We apply the video mask by simply dropping a subset of the tokens. Okay. We apply masking at the input of the X encoder and at the output of the Y encoder to construct contextualized targets. The encoder is parameterized using standard fit networks, while the predictor is a narrow transformer implemented using 12 blocks with an embedding dimension of 384. Taking inspiration from masked autoencoders, our predictor takes as input the sequence of embeddings produced by the X encoder, as well as a sequence of learnable masked tokens with positional embeddings indicating the spatiotemporal positions of the Y tokens. The output of the predictor is an embedding vector for each masked token. See Figure 3 for more details, as well as Appendix B. And they show here across and so they compare here methods pre-trained on images that and across data sets. They kind of show the performance here, which does do very well. Okay, so let's talk about label efficiency. So they find the model to be more label efficient. In particular, the performance of the largest model on K400 drops by 12% to 68%, top 1, when we reduce the number of labeled examples by a factor of 10x, from roughly 287 examples per class to 29. By contrast, the video masked autoencoder V2 drops by 30% to 37%, top 1. Video masked autoencoder drops by 15.9 to 62.3, top 1. And MVD drops by 14.6% to 62%, top 1. Now, how do they evaluate the predictor? Recall that the predictor network predicts the representations of a masked spatiotemporal region Y from a visible region X, given the positional information of masked regions. To qualitatively investigate the grounding of the feature space predictions, We freeze the pre-trained autoencoder and predictor networks and train a conditional diffusion decoder to map the predictions to interpretable pixels. Notably, the decoder is only fed the representation predicted for the missing regions and does not have access to the masked regions. Given a masked video, we use the model pre-trained to predict the representations of the missing regions, then use the decoder to project the representation onto pixel space. Qualities that are common across samples represent information that is contained in the picture or predictor representation. So the way they do this is essentially have a decoder or a diffusion-based decoder actually generate the representation back into pixel space. And this is how they evaluate the predictor. This is a very interesting way of evaluating the predictor. And this actually does make sense. Hold on, how do they... given a masked feature representation, indeedly grounded specifically. Okay. Very interesting. Okay. So, this is V-JEPA, as we see here. Very interesting network from Facebook research. You can actually check out the code at Facebook research/JEPA. Very interesting work. I probably will look into the code later at some point, but if you are interested in going through the code, feel free. And you can find the paper just on their website. Yeah, very interesting stuff. I'm very interested in seeing what this style of self-supervised learning can actually bring about in terms of machine understanding, because this is such a fundamental question that we cannot really crack beyond beyond generative approaches, which are prone to hallucination. What can you do? So very interesting stuff. It is halfway through the hour. I don't have anything else planned, so I'm probably going to end the stream here. Thank you everyone for tuning in. I will see you all on Monday, same time. I'm gonna continue working on the multimodal code. I need to read through LLaVA, and maybe we could do I could do a show and tell style paper. And if there are any other papers that you're interested in reading, just let me know, and we can go through it. Same old, same old. So thank you all for tuning in. I will see you on Monday. Peace.